So 8.1 is the exponential function. So we're going to do a couple different things with exponential functions. We're going to be looking at exponential growth and decay. We're going to be looking at their graphs. We're going to look at some of the properties of the log function, expanding and condensing, and we're going to be solving equations that have the variable x that you're looking for in the exponent. So the exponential function, the general exponential function equals y equals a b to the x power. The important thing is this, that exponent is the variable. Okay, so instead it's kind of a little different to look at because usually the x is with all the other ones. This time it's above in the superscript with the exponent. So we do have a couple more things we have to do. In this section we're going to look at the graph and the basic exponential growth and exponential decay. So you should have already done a little bit of graphing, know the general shape of the exponential growth and exponential decay, and just all the general functions, general parts of the graph. The properties that we're going to look at, remember, all these are going to be based off of that equation, y equals a b to the x power. A is the y-intercept. Okay, so as long as, and we're not based off of these also if they're not being transformed. These are the general functions, the general shape of the exponential. A is going to be the y-intercept. So whatever that a value is in the equation, that's where it's going to cross the y-axis. Okay? It will never cross the x-axis. And that's important when we start talking about decay. Okay? It might get closer and closer to the x-axis, but it never crosses it, it never touches it. Okay? It keeps getting closer and closer. The distance between the two gets smaller and smaller, but it never gets to zero. If a is positive, the graph is above the x-axis. If a is negative, the graph is below the x-axis. And that's really just looking at the flipping reflection over the x-axis, just like we did in the parent function back in chapter 7. And if b is greater than 1, the graph moves away from the x-axis to the right. If b is less than 1, the graph moves away from the x-axis to the left. And what we mean by that is, where does it start curving up? Is it going to the left or is it going to the right? Now what I'm going to ask you to do is by looking at an equation, can you tell me what the y-intercept is? Is it above or below the x-axis? And does it move to the left or right away from the x-axis? So looking at this one here, okay, the three things. The y-intercept is going to be 4. Okay, so the y-intercept, I don't want to say y equals, that looks like an equation. But the y-intercept equals 4, 0. Put it as a point there. Is it above the x-axis? 4 is positive, so yes, it is above. And the last part, it's 1.9. So 1.9 is greater than 1. That means it moves to the away from the x-axis to the right. Okay? So that graph, you should just with those points know, okay, it's crossing at 4, 0. It's above the x-axis and it moves away to the right. So it would look something like that, away from the x-axis, up and to the right. Here we have y equals 0.8, 2 over 5 to the x power. So again, start with the y-intercept. We have, 0.8. So actually, I want to go back and switch this. That would be the x-intercept. We have 0.4. Sorry, that was my mistake there. Okay, so we have a positive 0.8, so again it's above the x-axis. And 2 over 5 is less than 1, so this time it's moving away to the left. And what we mean by that is, if there's our coordinate plane, this is going to be going up and to the left this time. Okay, so these two graphs, okay, these are our two basic functions that we're going to be looking at. We have exponential growth, where it's getting bigger and bigger, increasing as the x value increases. And here, it's getting smaller and smaller as the x value increases. So this is on the exponential decay. Okay, so this is something you're going to have to be able to do, picking out these three, answering these three questions just by looking at the graph. Here we have asymptotes. Okay? Now you're going to talk much more about these when you get to pre-calculus and calculus. This is a line that the graph approaches as it moves away from the origin. So if we are looking at exponential decay, coordinate plane again. Exponential decay has a graph that is starting up high and going down. It's getting closer and closer to that x-axis. That x-axis would be the asymptote. Okay? It's getting, as it's moving away from the origin 0, 0, it's getting closer and closer. In this case, it's not going to touch. Okay? It's never going to get to the x-axis, but the x-axis would be considered the asymptote. Okay? So what you need to know about asymptotes is that the definition, a line that a graph approaches, it moves away from the origin, and be able to identify them. If the graph is getting closer and closer to a line, that's considered the asymptote. Again, you'll talk much more about those when you look at pre-calculus and calculus. For right now, the definition and just look at the graph identifying is what I want you to be able to do. Okay. Now we're not getting into basic, actually I'm not going to call them basic. I'm going to say they're a little more complicated than the general form of exponential function. Exponential growth, y equals a, 1 plus r to the t power. When an amount increases by the same percent each interval, and that percent is important. It's not going to be a set value. This is a percentage. The value that it increases by changes each time because the percentage, say, if you have a larger number, 10% of a larger number is going to be bigger than 10% of a smaller number. And if your number keeps getting bigger and bigger, that means that 10%, the value of it is getting bigger and bigger. Now the pieces to this. A is considered your starting or your initial amount. Okay, so I'm going to put that as your start. Okay, that's how much you have at the beginning, at the very beginning. R is your rate. And not always, but usually you're going to see that as a percent in the problem. And T is going to be time. Now, I can't tell you time is always going to be years, minutes, hours. It's not a change. Read the problem carefully and see what it's counting by. Now, that 1 plus r has a special name. The 1 plus r, the whole thing is considered the growth factor. Okay. So if you see a problem and it says the factor is 1.36, that's the whole part that's inside the parenthesis. If it just says, okay, we have a rate of 36%, well, that's the R. So you have to read the problem carefully. It's very important you read it carefully and identify it. Is it talking about the rate or is it talking about the factor? Now, types of problems you're going to see. There are 315 kids in the 12th grade. That number is increasing by 3% each year. How big is the class in 5 years? Well, our A, our starting amount, is 315. That's how much it's starting with. Our rate is 3%. I'm automatically going to start putting this as 0.03. That's what you need to plug it in as the formula. Okay, so remember, change that percentage into a decimal. And time, they're asking for 5 years. Right? So there's the three pieces we need. So if we were to plug this into our formula, y equals 315, 1 plus 0.03 to the 5th power. I'm not expecting you to be able to do these in your head. Plug it into your calculator and see what you get. For this one, I need to take a look on my answer key here. These are going to be estimates, so I'm not expecting a perfect answer. I know you can't have a 0.3 of a person. Plugging this in, you should get 365.171 students. Okay? I know you can't have 0.171 students. I want you to write down what the calculator gives you. Okay? So take a second, plug that in, and see if you can match that answer there. Okay? We had our starting amount, our rate, and our time. They're the three pieces you're going to need to find. The fungus on Bill's big toe weighs 0.05 grams. Its weight is increasing by 15% each week. How much fungus is on Bill's toe in 3 weeks? Well, again, our starting amount is 0.05. Our rate is 15%, so I'm putting 0.15. And this time our time is in weeks. This is what I mean. It's not always going to be years. The kid's problem before was students' problem was in years. This is in weeks. and we're looking at 3 weeks. Okay, so plugging this in again, y equals 0.05, 1 plus 0.15 to the third power. And we have, for our answer, 0.076 grams. Okay, make sure you're labeling your answer some way. I'm not looking for a novel explaining it, but some kind of units, 0.076 grams of fungus for Bill's toe this time. Okay? So that's exponential, or 2 examples of exponential growth. Okay? Exponential decay. Definition is basically the same thing, except when an amount is decreased by the same percent each interval. So we have y equals a, 1 plus r to the t power. Now, much of this is going to be the same. A is our starting point again. R is our rate. Again, usually going to be a percentage. T is going to be our time. And this time, 1 minus r, this is called our decay factor. Now, the other thing I'm going to point out here, for growth, you can get bigger and bigger all you want, okay? But for decay, the R has some boundaries. R has to be less than 100%, okay? So R is going to be greater than 0, but it has to be less than 100%. Now why? Think about why that has to happen, okay? Exponential decay is getting smaller and smaller, but it's never going to get to that 0. We talked about that when we looked at the graph. An example of the graph would look something like this, okay? Where it gets smaller and smaller, but never gets to that x-axis, okay? If the percentage is 100%, say you have 100%, or let's say you go on a field trip and you were losing 100% of your class every hour. Well, in 1 hour, if 100% of your class is gone, you have no students left. Everything is gone. The graph wouldn't gradually go closer and closer to the x-axis. If you lose 100%, sorry, I dropped my marker, you're starting at some point and you're going right down to 0 in one interval. Okay, so there's no gradual decline there. The 100%, you can't reach that 100% because everything's gone. You always have to have a little something left over. So if you're losing just, even if it's 99.9999%, there's always that little bit left over. And that's the important thing with exponential decay. There's always going to be that little bit left over. And yet for growth, R really doesn't have a boundary, okay? It can be, I mean, you can gain by 200%, 300%, 500%. You'll be increasing very quick. You just have to think about how much it's increasing by. So here's our example. The population of Smellyville is currently 42,000 people. People are leaving and the population is decreasing by 7% each year. How many people live there in 7 years? Starting amount is 42,000. The rate, saw it here, 7%, so I'm going to put it as 0.07. Our time is 7. 42,000. 1 minus 0.07 to the 7th power. So just make sure you're watching adding and subtracting. A lot of times people, for some reason people like plus is better. You're just going through it, you might put 1 plus 0.07 by accident. Remember, it's decay, it's decreasing. So you're going to be subtracting that 1 minus r. And if you plug this one in, you should have about 25,271.437 people. Okay. So there's an example of exponential decay. We did exponential growth, exponential decay, and we talked about the graphs a little bit. Okay. So the next video, the examples are a little more complicated. Nothing crazy, but a little more algebra is needed to solve these problems.